Hi folks, we're going to take a look at the solution to the February 11th homework number 1. Okay, so they give us this position function and they ask us a whole bunch of questions. So let's take a look at the first question. It says determine the velocity and acceleration function. So that's pretty easy here because it's just a polynomial. So the velocity, of course, is just the derivative of the position function. And so that will just be 4x cubed minus 20x, and then derivative of 9 is just 0. All right, and then the acceleration function is just the derivative of the velocity function, or the second derivative of the position function. And again, nice and easy, 4 times 3 is 12x squared, and then minus 20. All right, oh, sorry, minus 20, not 120. Okay, so let's keep solving here. Part D says determine the times at which the object is moving toward and away from the point of reference. Okay, and this is where we have to remember how we determine that. It's not enough to just look at the position function or the velocity function. You have to consider both. So what we found was that the object was moving, so let's say here is my point of reference. Okay, it's moving toward the point of reference when the position and velocity have opposite signs, and it's moving away from the point of reference when they have the same sign. So that means this whole thing is predicated on determining the signs of these functions. So of course, to do that, we're going to have to determine the zeros. I don't have to worry about asymptotes because these are polynomials. All right, so let's determine where s at t is equal to 0. So I'm going to factor this, and I see that I can factor it like a trinomial. So this is going to be x squared minus 9 times x squared minus 1. And then I can factor, these are both difference of squares, so we have x plus 3, x minus 3, x plus 1, x minus 1. Okay. And then for the sign, well, let me just draw one here. I'm actually going to draw a second one later on. You'll see why I draw a second one. But for s, here I've got -3, I've got -1, I've got 1, and I've got 3. And I use the fact that this is a quartic with a positive leading coefficient. So I know that the quartic would look something like that. So from here, I can easily determine positive, negative, positive, negative, positive. Okay? But of course, when I draw my official one that I'm going to use later on, I'm only interested in numbers greater than 0. So I'm not interested in t values less than 0. All right, so let's do the same thing now for velocity. So we want the velocity to be equal to 0. And again, this is fairly easy because I can just factor out a 4x. Oops, 4x, and what am I left with here? I'm left with x squared minus, and if I factor out 4x, I'm just left with 5. Okay, so here, x equals 0. We know there's going to be an x-intercept. Okay, and here I have x squared minus 5 equals 0. So in other words, x squared is equal to 5, and x squared is equal to plus or minus root 5. Now I know I'm not going to be interested in the minus root 5, but it will be helpful to sketch my my number line here. So what do we have? We have negative root 5, we have 0, and we have root 5. And so now what I'm going to do is take a look at what I have. I've got a cubic with a positive leading coefficient. So I know my graph would look something like this. So that means between 0 and root 5, it's negative, and then from root 5 on, it's positive. And I don't care about anything to the left of that. Okay, so now what I'm going to do to make this easy to kind of evaluate, I'm going to place these number lines one on top of the other. So I'm going to take my s at t, okay, again, started at 0, and create my number line here, and I see that I have to consider t equals 1 and t equals 3. And we said that from 0 to 1, it's going to be positive. From 1 to 3, it's going to be negative. And then from 3 on, it's going to be positive. And then I'm going to do the same thing underneath, keeping everything with the same scale. I'm going to do the same thing with the velocity function. Okay, so here we saw we have 0 and we've got root 5. So root 5 is about, I think it's probably around 2.2. So it'll be somewhere here, I suppose, root 5. And then we see that it's going to be negative to the left and then positive to the right. And so now what I'm going to do is I'm just going to draw lines at all these places where changes occur. Okay, so I know that between 0 and 1, the signs are opposite. Okay, so between 0 and 1, what's happening? The signs are opposite, so I'm moving toward the point of reference. Okay, let's go to the next one here. From 1 to root 5, I see that the velocity is still negative, but now the position is also negative. So since the signs are the same there, it's going to be moving away. So that means that from 1 to root 5, it's going to be moving away from the point of reference. And then let's look at root 5 to 3. Okay, again, the position is still negative, but now the velocity is positive. So from negative root 5 to 3, they're opposite, so I'm going to be moving toward. And then greater than 3, they're both positive, same sign, so we're going to be moving, excuse me, away. Okay, so notice here I've been able to do all this analysis by just looking at the signs of these two. All right, so if we take a look at part C, it asks us to determine the times at which the object is speeding up or slowing down. And in order to do that, we have to do something very similar, except with the velocity and acceleration. Okay, so I'm going to start by determining when the acceleration is positive and negative. So here I've got, so this is for C, I've got A of t, determine when that's equal to 0. But A of t here, I can just factor out, I guess I can factor out A4, okay? And what am I left with? So it looks like I'm left with 3x squared minus 20 divided by 4 is, 20 divided by 4 is just 5, okay, equals 0. And so this is going to be x squared has to be equal to 5 over 3. Just solve this equals 0. So x has to be equal to plus or minus square root of 5 over 3. Okay, and if we draw ourselves a little number line here, okay, we notice that this is just a quadratic with a positive leading coefficient. So if this is negative root 5 over 3, and this is root 5 over 3, okay, I know that it's going to look like this. Okay, but since I'm only interested from 0 to infinity, it's going to be negative in this interval, positive in that interval. And so as not to have to redraw this again, underneath my velocity function, I will now draw my acceleration function. Okay, so I'll just take a look here at what root 5 over 3 is equal to approximately. So 5, oops, made a mistake, 5 divided by 3. All right, so that's about 1.3. Okay, so remember this was about 2.2, so 1.3 would be somewhere here. So this is root 5 over 3. And we said that it was negative on this side and positive on that side. Okay, so I'm going to do the same thing as before. I'm going to do from 0 to root 5 over 3. I see that they're both negative. Okay, so when the signs are the same, it's speeding up. Okay, so from 0 to root 5 over 3, it's speeding up. Okay, then we'll go to root 5 over 3 to root 5. We see that the acceleration is positive, but the velocity is negative. They're opposite, so it's slowing down. So from root 5 over 3 to root 5, it's slowing down. And then lastly, from root 5 on, they're both positive, so it's speeding up. Okay. And then finally, we can get to the last question, D, which says, what happens to the velocity as time goes on? Okay, so when you hear words like as time goes on, I'm hoping you're thinking end behavior. So all we have to do is look at our velocity function and think about what its end behavior is. And what do we see? That it's a cubic with a positive leading coefficient. So what's the end behavior going to do? It's just going to get larger and larger and larger and larger. Okay, so here velocity is going to be positive and getting increasingly larger. Increasingly, something like that, larger. Okay, in other words, v of t is going to be approaching positive infinity. Okay, so just to recap, again, clearly we're going to use our velocity and acceleration. A lot of the questions here involved working with the signs of the function. Hence, I was just recycling all our tools for determining the sign of the function. And a good trick when I have to compare two functions at a time is to just draw them one on top of the other. Okay, that's it for this one.